Hi everyone and welcome to Tutorial 6. In this tutorial, we'll briefly review how to interpret logistic regression output, including the log odds of an outcome, and how to estimate odds ratios and the odds of an outcome. We'll also discuss the link between odds and probability, how to identify confounding, assess model fit, and identify effect modification with logistic regression. Remember that with linear regression, we were estimating the conditional mean, the mean outcome conditioned on the x's. But with logistic regression, we're estimating the log odds of the outcome. So all of our estimates are interpreted as the log odds with logistic regression output. In the last tutorial, we used an example where we had a single binary explanatory variable of weight, comparing those over 170 pounds to a reference group of under 170 pounds. The coefficient for this variable tells us the difference in the log odds of CHD between those greater than 170 pounds versus those less than 170 pounds, and is interpreted as the log odds of CHD is 0.53 higher for those greater than 170 pounds compared to those less than 170 pounds. The p-value associated with the weight variable is a test of significance for that variable. The null hypothesis is that there's no difference in the log odds of CHD between those greater versus less than 170 pounds, or that the difference between these groups equals 0. The alternative hypothesis is that this difference in log odds does not equal 0. Based on our output here, we would say that given that the p-value associated with the weight coefficient is less than 0.05, we reject the null hypothesis and have evidence to suggest that the difference in the log odds between those greater versus less than 170 pounds does not equal 0. As we talked about, the log odds are not the most intuitive to interpret, but we can calculate the odds ratio for a given x variable instead of discussing the change in the log odds. To do so, we simply exponentiate our coefficient. In this example, this tells us that those who are greater than 170 pounds have 1.7 times the odds of CHD compared to those less than 170 pounds. Or we can also say that the odds of CHD increase by 70% for those who weigh greater than 170 pounds versus those less than 170 pounds. We also learned how to estimate the odds of an outcome. For the reference group of less than 170 pounds, the log odds of the outcome is the intercept value, and the odds is this value exponentiated. For the group of interest of greater than 170 pounds, the log odds of the outcome is the intercept plus beta 1. And then we exponentiate this total to get the odds. For example, we could say that the odds of CHD for an individual greater than 170 pounds is 0.12. We can also estimate the probability of an outcome with our output, which is more interpretable than the odds. So how do we do this? Luckily, this is pretty straightforward. As I mentioned last week, odds and probability are mathematically related. Odds can be computed from probability and probability from odds. So if we estimate the odds of an outcome like we did on our previous slide, we can convert this to the probability of an outcome with the formula odds over 1 plus the odds. Or we can use our estimated log odds of the outcome and convert this to the probability of an outcome with the formula exponentiated log odds divided by 1 plus the exponentiated log odds. This slide is just to show the math of how odds and probability are related. You don't need to memorize this. It's just here in case it helps your understanding of the link between odds and probability. So let's revisit our same example and look at how we would calculate the probability of CHD. Since p equals exponentiated log odds over 1 plus exponentiated log odds, we plug in our log odds values from our output, and this gives us a probability of the outcome of 0.064. We follow the same process for an individual greater than 170 pounds and get a probability of 0.10. We would interpret this as the probability of CHD for an individual greater than 170 pounds is 10.4%. This slide summarizes the odds and probability of CHD for each of the two weight categories. As a couple of side notes, recall that we can't estimate the probability of an outcome given exposure or the relative risk with case control studies because the researchers have determined the number of cases in the study. We can estimate the probability of exposure given disease and the odds ratio with case control studies though. And you'll recall that the odds ratio is a good approximation of the relative risk when the prevalence of the outcome is low in the population. So now let's turn to the CHD data again, and this time our research question is there a relationship between smoking and CHD? Smoking status, yes versus no, is our explanatory variable of interest. CHD is our binary outcome variable, yes versus no. So because we have a binary outcome, we can use logistic regression. And this is a comparative or effect size model because we're interested in the relationship between a single X variable and Y. We want to include other explanatory variables in our model in order to get the least biased estimate of the relationship between smoking and CHD. So which explanatory variables should we think about including in our model? Let's take a look at the variables that are available in our dataset. As you can see, we have many different variables that we could potentially include in our model. But as we've talked about, we don't want to include all of these in our model. We want to be selective in the variables that we consider and follow a systematic process for building our model. Like with linear regression, we want to adjust for any confounders by including these in our model. Potential confounders can be identified from previous studies, subject area knowledge, and/or statistical considerations. So what the numbers are showing, which can be especially important in new study areas. But we don't want to rely exclusively on numbers. Confounders should also make sense theoretically. We can also include predictors of CHD in order to improve the precision of our estimate for smoke. But we might also choose to exclude a predictor from our model. Either decision is fine as long as you clearly justify this. And finally, we can also include variables for face validity. For example, age or gender may not meet our statistical criteria to be considered as confounders, but we might want to include these because these factors are often important determinants of health. We also want to take care to avoid collinearity. For example, in this dataset we have 4 different weight measurements, so we'll only want to include one of those at maximum. So first let's start with a simple logistic regression model that only includes our primary explanatory variable of interest, smoking. How would we interpret the smoke coefficient here? We would say the log odds of CHD is 0.63 higher for smokers compared to non-smokers. How would you calculate the odds ratio? You would exponentiate the smoke coefficient. This gives us an odds ratio of 1.88. So we would say that smokers have 1.88 times the odds of CHD than non-smokers. We can also calculate a 95% confidence interval for our odds ratio. To do this, we can either use R, or we can do this by hand by multiplying the standard error of beta 1 by 1.96, adding and subtracting this value from beta 1, and then exponentiating to get the lower and upper confidence limits. We can then claim that we can be 95% confident that smokers have an odds of CHD that's between 1.44 and 2.44 times the odds of non-smokers. Detecting confounding follows the same principles in logistic regression as linear regression. Does it meet the definition of a confounder, both theoretically and/or supported by the data? So does it make sense that the variable is associated with x1 and a predictor of y, but not on the causal pathway? And how are these variables associated when we look at bivariate associations or plots? Also, like linear regression, we're looking for a change in beta 1, with the same rule of thumb of a greater than 10% change in beta 1 indicating confounding. But the first criteria of meeting the definition of a confounder is the most important with logistic regression because we're dealing with a logged outcome. So what do you think? Could age be a confounder? Conceptually, this could make sense. Age is likely a predictor of CHD, so as age increases, the likelihood of CHD probably increases. Age could also be positively or negatively associated with smoking, depending on the population, and it wouldn't make sense for age to be on the causal pathway between smoke and CHD. Let's check out the bivariate associations between age and smoke and then age and CHD to see if our theory is supported by the data. As you can see, a two-sample t-test suggests no significant association between age and smoke. The mean age is similar for smokers and non-smokers. If we look at the results for a two-sample t-test of the relationship between age and CHD, we can see that there's a significant difference in the mean age by CHD status. Those with CHD tend to be older than those without CHD. So, does age meet the definition of a confounder? Let's recap. Conceptually, we said that it could be a confounder, but this didn't hold up in our bivariate analyses. Age was significantly associated with CHD, but not with smoking. Let's take a look at the change in our smoke coefficient when age is added to the model. Recall that in our simple logistic regression model, the smoke coefficient was 0.63 and its standard error was 0.13. When age is added to the model, the smoke coefficient is 0.64 and the standard error is 0.13. So there's not much of a change compared to the reduced model. So based on the lack of the coefficient change and the bivariate associations, it doesn't look like age is a confounder. But we should also see if including age makes our model better by increasing predictive power. This could provide some evidence for us to keep it in the model. We can test this by looking at the likelihood ratio test, or AIC. If we compare the AIC of the two models, we can see that it's lower with the second model, suggesting that this model is better. We can also use the likelihood ratio test. The likelihood ratio test is equivalent to the partial F-test in linear regression. And in fact, the partial F-test is a form of likelihood ratio test. Like the partial F-test with linear regression, the likelihood ratio test can be used only to compare nested models. It compares the residual deviance of the reduced and full models. Recall that the residual deviance is the variation not explained by your model, or the error. How far observed values deviate from expected values. So this test tells us if the error is reduced by adding or removing variables from a model. As a side note, we can also use the likelihood ratio test to assess the overall model fit. This is similar to the F statistic that's included in your model output with linear regression. It's calculated as the null deviance, so the deviance of a model with no variables, minus the residual deviance of the model. It tells us, is this model better than no model? So it's not very useful. So let's take a look at the results of our likelihood ratio test for this example. So we can see that the p-value is less than 0.05, so the residual deviance of the second model that included age is lower. Based on this, we can reject the null hypothesis that the full model is not significantly better than the reduced model, and conclude that we have evidence to support our alternative hypothesis that the model that includes age is significantly better. So what do we do? Should we keep age in our model or not? We could argue either way. We saw that it didn't really meet our criteria for a confounder numerically. The smoke coefficient didn't change much with it included, and even though age was associated with the outcome, it wasn't associated with smoking. So for these reasons, we might not want to keep it. But we thought that it could make sense theoretically as a confounder, and we also saw with the AIC and likelihood ratio test that it improved the model. Also, age is often adjusted for in epidemiological studies for face validity, so that's another reason to keep it in. So you could argue either way, but for face validity, theoretical reasons, and because it improved the model, I'm going to keep it in our model. So let's take a look at measures of body composition again. We have 4 variables, so which variable should we use? Remember, we said that we should only include one of these variables because these are likely collinear. Let's compare a model that includes BMI to one that includes weight. The inclusion of these variables has a similar effect on the model. The smoking coefficient and the error are about the same. So how do we decide which one to include? We could compare the AIC of the two models. So remember that we can't use the likelihood ratio test because these aren't nested models. We can see that the AIC is slightly lower with the weight model compared to the BMI model, so we may want to go with weight. We could also check to see which best meets our model assumptions, which we'll discuss in an upcoming tutorial. It could also depend on how the variable is measured, or things like which is more recognizable or theoretically important. But I'm going to say that we should proceed with weight since the model that includes this has a lower AIC than the model with BMI. So going forward, our model will include smoke, age, and weight as explanatory variables. So you'll recall that age didn't clearly meet our definition of a confounder, but what if age is an effect modifier? So let's now try to answer the question, does the effect that smoking has on CHD depend on age? Like how we conducted a partial F-test with linear regression, we can use a likelihood ratio test to compare models with and without a smoke times age interaction term. We can see that our p-value is 0.271. So we would fail to reject the null hypothesis that the residual deviance is the same for the models that do and do not include the interaction term. The model that includes the interaction term is not significantly better. This suggests that age is not an effect modifier. The effect of smoking on the odds of CHD does not appear to vary or differ depending on age. So we don't have evidence to suggest that age is an effect modifier. There was no significant interaction between smoking and age. But for the sake of learning, let's say that our p-value for the likelihood ratio test was less than our significance level of 0.05. It wasn't, but let's pretend it was. In that case, we would reject the null hypothesis that the residual deviance of the two models were the same. This would suggest that the effect of smoking on CHD depends on age, that age is an effect modifier of the effect of smoking on CHD. This means that we would want to report on the effect of smoking for different ages. Anything we say about the effect of smoking on CHD needs to be age-specific. We can't simply use the getOR function in R to get odds ratios when we have an interaction term in our model. We need to do the calculations for the age-specific odds ratios by hand. So assuming that our interaction term was significant, let's proceed in calculating the smoking effect for different ages. Recall that when you have a categorical effect modifier, you simply calculate the strata-specific effect for each category of that effect modifier. For example, if your effect modifier was gender rather than age here, you would calculate the smoking effect for men and women separately. But because we have a continuous variable, age, in our interaction term here, we need to assign possible values to compare groups. For the purposes of this tutorial, let's just focus on two ages only, ages 50 and 60. We follow a similar process that we would if we were calculating an age-specific slope with linear regression. But instead of this slope referring to the conditional mean of y, this refers to the log odds. For 50-year-olds, we multiply 50 times the age times smoke interaction term coefficient and add this to the smoke coefficient. This gives us a log odds ratio of 0.67. For 60-year-olds, we follow the same process as with 50-year-olds, but substitute 60 in place of 50. This gives us a log odds ratio of 0.42. So we could say, for example, that among 60-year-olds, the log odds of CHD are 0.42 higher for smokers compared to non-smokers, adjusting for weight. But as we've talked about, interpretations of the change in log odds of CHD for smokers compared to non-smokers aren't all that intuitive to interpret. So compared to linear regression, we need to take an extra step to make this more interpretable. We need to exponentiate our log odds ratios to get odds ratios. For 50-year-olds, we get an odds ratio of 1.96, and for 60-year-olds, we get an odds ratio of 1.51. And I'd really encourage you to try going through this whole process and calculate these by hand. Our interpretation would be that among those age 50, smokers have 1.96 times the odds of CHD compared to non-smokers, adjusting for weight. We could also say that a smoker of age 50 has 1.96 times the odds of CHD than a non-smoker of age 50, adjusting for weight. And our interpretation of the age-specific effect for 60-year-olds would be, among those age 60, Smokers have 1.51 times the odds of CHD compared to non-smokers, adjusting for weight. So this is just a quick intro to logistic regression assumptions. The first is that the Y values are independent. And as with linear regression, we check this by examining the study design. So for example, twins would not be independent with a birth weight study. The second assumption is that Y is distributed binomial given X. We don't need to check this because we're using an outcome with yes versus no, so therefore Y is binomial. The next assumption is that the expected Y is a logistic function of the X's. In other words, the relationship between the log odds of Y is linear with X. So linearity is the main assumption that we need to check statistically. We need to check for linearity between all continuous explanatory variables and the log odds of Y. We'll go over how to assess linearity in tutorial 8. The next assumption is that the X's are fixed values, meaning that they do not change, which we know from knowledge of study design. And the final assumption is that the model fits well. This is another assumption that we should check statistically with something like a likelihood ratio test or AIC.
Thanks for watching our video. Stick around, guys, because we got lots more.